Hi everyone, and welcome to another video from Erik's Electronics Workbench. So on the bench today is this Atlas Sound Model CP400 2-channel commercial grade audio amplifier. Now what I know about the amp is that it doesn't work and that it powers on into the protection mode, or that there is some kind of an issue with that protection mode. Now to make the troubleshooting a bit more tricky, I've not been able to find a schematic or any service literature. Now I did notice the manufacturer still offers this model for sale at the time this video is being made, and it's an expensive amplifier, so I think it's definitely worth the effort to repair it. Now a key feature of this amp for commercial installations is the 25, 70, and 100 volt outputs for large distributed constant voltage sound systems. Now I'll talk about what constant voltage speaker systems are later in this video. And of course the amp can drive typical 8, 4, and 2 ohm speaker loads. So let's get started with the repair. So when I start the troubleshooting on an item like this, where I don't know the history behind it or how it's been used or treated over the years, before initially powering it up, I like to just make a quick inspection on the exterior of the device to make sure there's no serious physical damage, and then also become familiar with the controls and indicators. So on the top cover, there's some light scratches back here, but nothing really out of the ordinary for a used amplifier. Right here, I don't know if you can see on the camera, but there's a little bit of a bump that's poking outward, so I'm curious to see what's on the inside that actually caused that. If you can hear, it's a pretty heavy gauge of steel that's used on that cover, so it wouldn't bend very easily. So if something hit the top, you would think it would make a dent inward, but this is actually a bump from the inside poking outward, so I'll have to take a closer look at that. And looking at the front panel up here, there's some status indicator lights for channel 1 and channel 2, so the protection indicator lights up here, so if there's a problem, the protection mode kicks in. The limit indicator lights are basically a clip limiter, so if the amplifier is severely overdriven, it keeps the output from turning into a square wave. And then the signal indicator lights are just a confirmation that you have audio signal present, so when the audio signal hits a predetermined low level, those illuminate. You have to keep in mind that with professional audio, it is possible that this could be in an equipment cabinet. It could be a long ways away from where the speakers actually are installed, so you might not hear the audio playing even though there is audio that's active. And this, again, is just a nice confirmation that there is activity on the audio input signal. Over here, power switch and power indicator light, and a vent right here for the air probably is drawn in this direction and then usually exhausts out the back. Now if you're interested in the technical specs of the amplifier, I'll go ahead and put those up on the screen now so you can pause the video, check that out if you'd like. And I'll get the switch just flipped around here and take a look at the back. It's a pretty heavy amplifier, it's about 50 pounds. You can see that in the shot there. So the power cord is still bundled up just the way I received it. Like I say, I have not powered it up yet. For all I know, it could be a charcoal briquette inside, so we'll find more out when I take the top cover off. Now back here you can see channel 1 and then the channel 2 speaker outputs. So this has the 2, 4, 8 ohm connections over here. It's just a standard speaker connection. And then the distributed audio, the 25, 70, and 100 volt outputs are over in this side of the terminal board. Vent right here for the fan. You can't actually see the fan in here, so the fan must be somewhere in the middle back in here. And then the audio input section is over here, so you can see channel 1 and channel 2. So there's XLR connectors for the input as well as a terminal board. Now this has a pass-through connection for daisy chaining to other audio devices, so you have the input and then it comes back out again where it says through right here. Level control for each channel. Does have a nice detent when you turn them, so a very positive feel to them. And there's a mode selector switch down here for parallel, stereo, and bridged operating modes for the amplifier, so it just sets up the main operating mode. Now you'll notice there's no RCA connectors on the back of the amp. Because this is a professional or commercial grade amplifier, it uses balanced audio inputs, and RCA connections like you would find in a home type audio system are unbalanced. And unbalanced audio connections and long cable runs with unbalanced audio is very prone to picking up hum and noise. So again, with professional audio, it's very common to have long runs for the audio interconnects. Think about going across a stage or a studio. So balanced audio works by having the audio on 2 lines with a shield around it. And so the audio is on these 2 lines and it's not connected to that shield. And the electronics that are involved with that type of a connection, along with the balanced audio connection, is just very immune to picking up hum and noise and other problems. So it's basically exclusively used on professional audio. It also operates at a higher level than RCA connections that you would find in an unbalanced audio system, but you can connect an RCA type connection where it's unbalanced into this amplifier. You can do so by tying the negative connection over to ground and then applying the audio between the positive and then the ground connection. Again, the audio level is a little bit lower for unbalanced, but it will work out. You can turn the level up a little bit higher if necessary. You can also buy adapters that go from unbalanced to balanced on the XLR connectors. So the next thing that I'll do is get this top cover removed, and let's take a look around inside the amplifier. If everything looks okay and there's no major problems that are visually obvious, then we'll go ahead and power it up and start doing some troubleshooting. So there's 16 screws that hold the top cover in place, so they certainly didn't skimp on the hardware. Get these last 2 screws removed here, and then we'll see what the condition looks like on the inside. Alright, top cover probably just, slides back, like so. Get that out of the way. Wow, that actually looks a lot better than I expected on the inside. It looks really clean. See the fan, it seems to turn okay. Really no dust or lint on the fan blades. And the circuit boards down here look really clean. Wiring looks clean. I don't see anything that looks overheated at first glance. There's looks like 6 fuses on the circuit board here. I don't know if you can quite see them on the camera, but I don't think any of those are blown. The fuses look okay. Very large toroid type transformer for the power transformer here, and then these 2 transformers here would be for the distributed audio for that 2570 and 100 volt output. I'll talk a little bit more about that later in the video once the repairs are completed, and I'll do a demonstration and show exactly how the distributed audio works. But very large toroid transformers for the outputs right here. Oh, let's take a look and see what was causing that bump on the top cover here. So this cover was installed this way here. The bump is over here in this corner. And I think I see what's going on there. That's this bolt right here that holds this transformer in place. It looks like it probably bumped up against the inside of the cover. So I think what happened is that the cover maybe had something heavy that pressed down, and then it just caused it to press against that bolt. Seems tight, no issues there. So really not a problem. I can straighten that top cover out and get that little bump taken care of. But yeah, everything's looking really clean inside. I don't see any issues that are going on that would, prevent it from powering up safely, and then we can start the troubleshooting and see exactly what's going on. But yeah, it looks pretty good at this point. Now, I don't see the filter capacitors or any of the other electronics, and it looks like there's a circuit board under this steel plate right here that these transformers are mounted to. So it looks like all the other electronics must be under this area over here, because the heat sinks are here, and there's no capacitors over here, just one capacitor down here, and that's just for the filter on the AC line. So yeah, it looks pretty good. Looks like the output devices on the heatsink here, they're being paralleled, so pretty much to be expected with the power rating that the amplifier has. So there's 4 output devices over here, and then the other channels on this other heatsink here. You can see the heatsink is actually divided in the middle. It's 2 separate heatsinks for each channel. In the user manual for the amplifier, they kind of make a point about that the 2 channels are treated separately, that there's dual power supplies and kind of separate circuitry and everything for both channels. So it does look like they've incorporated that in this layout. Some thermal switches right here. Now it's interesting, there's 2 thermal switches on this one heatsink, and I can see a wire coming up here in this corner, so there's probably 2 more thermal switches on this other heatsink. Now this does have a dual speed fan, so maybe one of those switches is for the fan, and then the other is probably for the protection mode if there's an overheat condition. So I think at this point we should try and power it up and see what happens. So what I'll do is get this power cord unbundled, flip things around here, and try and power it up, and then see what we can do for the troubleshooting and see exactly how it's functioning or where the issues are at. Alright, I have the amplifier plugged into my isolation transformer, and that's an absolute necessity when you're working on AC line powered devices. So if you're following along, you're definitely doing so at your own risk. Be safe and take care, and know the safety precautions necessary when working on AC powered devices. On an amplifier like this, there's definitely high voltage DC that's distributed around through the circuitry, so you wouldn't want to come in contact with that DC voltage either. So again, you're definitely doing so at your own risk if you're following along and working on a similar device. Okay, let's power it up and see what happens. I'll reach over here. Wow. I'll shut that back off again. That's interesting. So that humming or chattering sound really to me sounds maybe like some relays. There would definitely be speaker protection relays. Now I noticed that the protection lights did turn on both channels, and that was mentioned that that was a fault, that the amplifier was on a protection mode, but That's a very odd sound. That doesn't sound like a transformer to me humming. It didn't blow any fuses. My isolation transformer is still on. The indicator light is turned on that, so no issues with a major overload, short circuit or something like that that can make a transformer hum really loud. So that's an interesting fault. I don't know what else would be causing that humming sound. And like I say, this would have speaker protection relays. If they're chattering, and the protection mode should lock in if there is a fault, so they shouldn't be cycling on and off, and certainly not rapidly like that. Let me grab my notes over here and take a look. So I did notice in the user manual it mentions some protections that the amplifier has. So there's an offset voltage protection, so if it detects a DC offset at the amplifier's output, it'll go into the protection mode. That certainly could be happening, you know, if there's an offset voltage, but it wouldn't explain that humming sound. If the heat sinks have an overtemp condition, it'll go into the protection mode, but there's certainly no excessive temperature because it's just being turned on, so that couldn't be it unless there's a faulty temperature sensor. So we might want to look at those temperature sensors or those switches. But again, it doesn't really explain that humming sound. They do mention that the transformers have a protection for overheating. I have to think that that's probably a bimetallic strip or like a temperature sensor that's embedded in the transformer. I don't see any wiring coming out of the transformers that would go into the protection mode on the transformer, so I think if that trips, it would just shut down the amplifier's operation, or the power would just cut out. A lot of transformers do have embedded thermal switches in them. They mentioned that there's a speaker overload protection, so it can detect if a high current flows out to the speakers, it'll shut down. Well, there's no load connected, so you know, if it's falsely detecting an overload condition, maybe there's a problem with the protection circuit itself, so that's something to consider. Power on-off protection, it probably just has maybe a slow turn-on protection or a thump type elimination, so that when it's turned on and turned off, you don't get that big thump out to the speakers. And it mentions the soft clip limiters, so we know that already from the input. That's not really a protection mode, that's just on the clip limit that it has built in that just prevents the output from distorting severely. So kind of knowing what it can protect against, the DC offset is something that I would look at first, and we'll try and take a measurement and see if that's actually occurring. Maybe it has a DC offset from a failed output device or some other part of the circuitry that isn't working right. But I'm very curious about that humming sound. That's really unusual. I've actually not worked on an amplifier that has done that before, where the protection mode is sort of chattering or turning on and off extremely rapidly. And you know, if a relay turns on and off very quickly, it would make a buzzing kind of sound, and that's what it reminds me of. I noticed that the fan was running okay. It turned on, and that fan, yeah, it turns okay in there. That noise I don't believe was coming from the fan. It's not hitting anything. So I think the next thing to do is to actually remove this area over here, get it set to the side so that we can see what's going on the electronics down here. We're going to definitely need access to all of that to do any kind of troubleshooting. So I'll work at some disassembly here, and then we'll take a look and see if there's visually anything wrong, and if not, of course, we'll start in on the troubleshooting and take some measurements. Alright, I have this metal bracket that holds those two toroid transformers turned upside down and positioned out of the way so we have access down to this main circuit board. Now with the weight of these transformers, it still wanted to kind of tip over. The transformers are resting on this edge right here. So I have a zip tie that's back there and it's holding it in position. So this can pretty much sit here. I think for the remainder of the troubleshooting, it's out of the way enough that we can gain access to what we need here. Unless I need to do something with this other heatsink, you know, this will be okay here. Now, oddly, I noticed that when I removed this heatsink here, you see how loose that is? There's screws on the bottom of the chassis that hold this heatsink, and they're extremely loose. And this one here seems a little loose too. I have no idea why those would have come loose, but they'll tighten those up later on. So looking at the main circuit board down here, we can see the power supply filter capacitors for each channel. So there's obviously a positive and negative rail, so 2 capacitors per channel. You can see there's room for more capacitors, and they're not populated in those areas on the circuit board down there. And it looks very modular. Everything looks like it plugs into the circuit board, just in various locations here where everything ties in. So it looks like it'll be easy to remove this circuit board. And I think we're going to need to do that because in this corner, you can't quite see it on the camera, but there's a power resistor back here, and this circuit board is discolored right around that resistor. indicating it's been very hot, and right next to the resistor is a capacitor. I can't imagine that capacitor, it's an electrolytic capacitor, and I can't imagine that it would be in very good condition given how hot it looks like that resistor has been. Now if you look above that, of course the heat is going to rise up above this resistor, and this vinyl boot right here is actually all discolored, and this one here a little bit, but this one very discolored right there. The vinyl boots back here on this one are not. And look at right here on this metal right here, you can see the discoloration right here. And that's right above where it would sit right here. So the heat rising up has basically discolored this area. Seems like a lot of excessive heat coming up from that resistor. Now, maybe that's by design. It may always run hot. But I have to think that maybe there's an issue going on right at the circuit board or that capacitor or something in that area. It definitely needs to be taken a closer look at. I can't test the capacitor without removing this circuit board. And I'd like to test that resistor as well. So the next thing that I'm going to do is remove this circuit board, and then I'll be back with that removed and we can take a closer look at those components. Okay, I have the main circuit board removed, as you can see here, and I'll explain what's going on with all these jumper wires that I have connected as well. Now, something that I noticed is that when the amplifier was first turned on and we heard that kind of odd buzzing sound, the protection indicator lights were turned on for both channels, and I thought that was a little bit unusual because it's unlikely that both channels would develop a fault and need to go into the protection mode. It is possible, but again, rather unlikely. So the circuitry is designed such that one channel could go into the protection mode, but it wouldn't affect the other channel. So they're not going to shut down both channels just because one has a problem. So I thought maybe there's a problem with a component that's common to both channels, or maybe there's a problem with the power supply or something like that. So my thought was that if this board was removed from the amplifier like you see here and could be powered up, it would be a lot easier to test it this way. And I can get to both sides of the circuit board and so forth. So in looking at the board, I studied the components, spent some time kind of tracing things around to see exactly what components had what function and so forth. And what I discovered is that there's basically three sources of power to the board. There's a DC supply to this area over here for one channel, goes to the DC rails over here. There's another DC rail that comes over to the other channel. And then there's an auxiliary AC winding, it's a center tapped winding, powers the majority of the low voltage circuitry over here. And that's what you can see is connected. So this connector down here was originally plugged into the board over here. So the white wire is the center tap, and then the outside of that winding is on the two yellow test leads. So I've just clipped it onto the board here, and that'll allow me to power up the board with just the low voltage portion and not have the DC rails powered up. Now, in examining the circuits further, I discovered over here that resistor that had gotten really hot, and you can kind of see the board is discolored and kind of yellowed down there. That's for the fan speed control, so that's the low speed, which it would be in most of the time. This other resistor next to it is a 33 ohm resistor, and that's for the high speed control. So they're basically just putting a voltage drop, and slowing the motor down that way. But that resistor has gotten extremely hot, so I think the wattage should be increased, and also maybe it should stand off the board a little bit higher. Now, right next to it is a capacitor, and this electrolytic capacitor right here is related to the speed control circuit, but all the electrolytic capacitors in here I've noticed are rated 85 degrees Celsius. A little bit disappointed to see that. I'd like to see 105 degrees Celsius, given that a lot of these are right near a lot of heat generating components, these heat sinks, this resistor, and that resistor has been smoking hot and it's right against that capacitor. I can't think that that capacitor would be in very good condition. So we'll check it out, probably just replace it. I can't think leaving it there would be a good idea at all. So over here you can see the AC voltage comes in, it goes through these two fuses for protection, goes to this bridge rectifier, these two capacitors for filtering, then we have two voltage regulators. This is a negative 15 volts, this is a positive 15 volt regulator, and then that goes off to the majority of this other circuitry over here. Now the relay here and this relay right here, those are the speaker protection relays, and I'm sure that's what we're hearing buzz because there's nothing else in here that's mechanical that can make that noise, and it's not the fan motor that's making any noise. But these are 24 volt relays, so I don't believe these are being powered through these voltage regulators over here. I think they're being powered directly off of this AC voltage that's coming in here. I haven't traced that out yet, so I'm not sure yet if that's exactly correct or not. But again, it would be unlikely that they would power, a 24 volt relay off of 15 volts. It may not pull in correctly, and they probably wouldn't do that. Now, looking at the circuitry around these relays, you can see there's two transistors right here. There's a diode, this electrolytic capacitor, there's a Zener diode right here, a resistor, and there's actually a diode back there. You can see that's duplicated over here. There's a diode right there, that same electrolytic, the two transistors here, the same Zener, resistor, and so forth. So you can see things are duplicated, and you can basically see it's divided down the middle here. A lot of this is audio circuitry, and here these are driver transistors. But again, looking at what is related to these relays, this is a control. These two transistors right here turn on this relay. Those transistors are connected in series. I haven't traced out everything yet, but it looks like they're connected, I believe, in series for switching purposes. So something that I noticed is that when I powered up the circuit board, one of these relays clicks in right away, and the other one, there's a delay. Well, it's normal that there should be a delay because it prevents turn-on thumps on the output to the speakers. So it's interesting that one of these doesn't even have a delay and that the other one does, but they both seem to chatter. Whenever you have a circuit that has a delay built in, there's usually a capacitor involved, and I believe that's what this electrolytic capacitor right here is for, and then this one over here. Again, these are 85 degrees Celsius, and it's right against a heat sink. I would be very suspicious that this capacitor has developed a problem, and this one right here as well. So we'll measure those and see if there's an issue going on. Now, something else I noticed is that they pick off one of the AC windings and run it over here through that diode back there, that diode right there. Then it goes into some circuitry and ultimately comes over to this electrolytic capacitor and then to this one of these transistors. I believe that's how they're creating the delay. It's basically slowly charging up this capacitor and then allowing one of the transistors to turn on. That could also explain the buzzing sound that we're getting out of these relays. If they're chattering and turning on and off rapidly, perhaps these capacitors have failed and the time delay is not working correctly. So again, I'll measure those capacitors in just a moment. But first, let me turn on this circuit just the way you see it here. And you'll be able to hear that the relays don't click in together. You'll hear a slight delay and then the second one will click in. So I'll reach around over here and turn it on. And I'll do it one more time. I think you can probably hear that. There's a delay and then the second relay clicks in. When I'm listening to it, it sounds like this is the one that has the delay that may be working closer to normal, but it's chattering as well. So I'll get things disconnected. I'll turn the circuit board over and let's take a measurement on those electrolytic capacitors and see what the condition is. I did measure the output of these regulators and it is correct. No issues with that. And again, I don't think they're being used to power up any of the circuitry anyways, but both of these did measure okay. And I let the circuit run for a little bit in kind of this odd state where it's buzzing and making noises. And I didn't detect anything getting overly hot or any problems like that. These regulators seem to just get warm, but not anything excessive. So it doesn't seem like there's any short circuits or anything pulling down any of the voltage rails or anything like that for this portion of the circuitry. And one more thing that I should add, the reason that these test leads right here are clipped on, and then you can see the end of the test lead doesn't go anywhere right here, and same with the little red test lead. All I'm doing is using the one end right here as a jumper to bridge two of the pins on that connector and two of the pins on that connector. The reason is that actually runs off to the temperature sensor. Put the camera up a little bit here. So this temperature sensor right here with the green wires, and then there's another one over here with the green wires on it. And those are wired in series with the coil that's in the relay. So if you break this connection and don't have it closed, the relay will not energize. So these are normally closed. If there's an overtemp condition, they would open, and then that causes the relay to also, shut off, and basically its contacts would then open. The other thermal sensor that's on this back one here, move the camera up a little bit higher, but there's the green wires here. So this is for the relay on the one channel. This controls the relay on the other channel, or is in series with it, I should say. This temperature sensor right here with the gray wires on it is for the fan speed control. So it's related to that circuit. Okay, let's test those two electrolytic capacitors. One of them is right here on the board. So yeah, that's suspicious. Definitely need to remove that one and just measure it out of circuit, but that doesn't look too good. And the other one is right over here. Interesting. So those circuits are identical and the result is different on each. Very suspicious. It's basically telling us there's an extremely high ESR and it can't even measure the capacitance. Try that one more time. Yeah, same result. Just go back over here, try this one again. Yeah, both of those very suspicious, so I'll go ahead and remove both of those electrolytics and we'll just check them out of circuit and see what happens. Okay, I have the 3 electrolytic capacitors removed. You can see them right there. So each of these is 100 microfarad at 25 volts, and then this one is a 47 microfarad at 50 volts. Now, this is part of the fan speed control circuit, and then each of these is used on the turn-on delay circuits, one for each relay. So let's test them and see how they perform. Wow, that one's definitely faulty. No question about that. That one's also faulty, so that would certainly explain why those relays were chattering. And basically that protection mode, I think, is what was happening, is that the turn-on delay wasn't working right, and then it was just keeping it in the protection mode. So I think if it's working correctly, the protection mode indicator lights will turn on briefly at power up while the delay is occurring, and then they should turn back off. We'll see if that actually happens, but no question that those are definitely defective. And let's take a look at this one here. Yeah, it's defective as well. Again, this one was right next to that resistor that's getting so hot, so no surprise that it would also fail. I have to question some of those other capacitors that are on the circuit board. I might go through and just kind of check a few of the others and just see if there's any other issues going on. But I'll go ahead and get these replaced first, and then we'll see if the circuit starts performing correctly, how it's operating, or if there's any other problems, and then we'll go from there. So one step at a time, but I'll get some new capacitors installed and then I'll be back. Okay, I've replaced the 2 100 microfarad capacitors that are in the relay control circuit that would affect that startup time delay. So you can see the one capacitor right there and the other one right there. So each of those capacitors is 105 degrees Celsius rating, so definitely an upgrade from the original 85 degrees Celsius ratings. They're Panasonic brand, very high quality capacitors, so they'll be good for the long term. So let's power up the circuit and see if it's functioning correctly or if there's some more troubleshooting. So the connections are the same as I had previously. You can see coming off of that secondary winding here just to power up the circuit board, and then again jumping across 2 pins on that connector and then 2 pins on this connector just to bridge across, because those would go off to the temperature sensors on the heatsink, so that's why there's nothing on the ends of these test leads here. It's just bridging that the jumper between those pins. Okay, so I'm going to reach across here and turn on the power, and we don't want to hear anything. If it's working correctly, there should be a delay and then the relay should click in. So power is on. There it is, the relay's clicked, so there was a nice time delay. That would let the amplifier settle down. It would prevent any turn-on thumps or any noises out to the speakers. So that seems to be working correctly. It's absolutely quiet. There's no chattering or humming noises. All that problem is taken care of now. So it seems to be working well. I'll grab my digital multimeter here. Get this into the shot here. I think you can see the numbers on there. So let's take a voltage reading across the coil. Now, there's a diode right there, and then you can see there's a diode right there next to each relay. So those are the voltage kickback suppression diodes. So when the relays are switched off, it just suppresses the kickback voltage that is generated across the coil. So because those are directly across the coil, we could actually measure that coil voltage. So let's see what we have on this one here. Yeah, 30 volts, almost 31. So that's what I was thinking. Those are not powered through these voltage regulators that are the 15 volt plus and minus regulators over here. It's interesting though, they're powering this with 31 volts and they're 24 volt relays, so a little bit on the high side, but not much really could be done about that. Let's see here if I can get over to this one here. Yep, 31. Disregard the negative, it's just because my test leads are flipped around on that polarity there. So perfect, each one has voltage and it's the same. Let's try something else here. If I can get a reading on this. I'm going to turn this back off again. Okay, watching the digital multimeter, let's watch for that time delay when that voltage turns on. So amplifier is on. There it is. Perfect. Let's try the other one. Switch this back off again here, just to make sure that both of them do in fact have a time delay. If I can reach in here and get a connection on there. All right, here we go. There it is. Perfect. No issues with that. Definitely a time delay. It's about equal, I would say, on each one. So that's working very well. So the next thing that I'm going to do is look at relocating this power resistor for the fan low speed. I don't like that it's on the circuit board. It's causing damage to that board. It's running extremely hot. So I'm going to look at mounting that as a chassis mount type power resistor. See if I can find a better location within the amplifier to mount it, maybe something on the bottom of the chassis, something like that. So I'll be back when that part is done. And in looking at the rest of these capacitors on this board, I think the best thing to do would be to actually replace all the other electrolytics. Given that 3 of them have already failed and all of these are 85 degrees Celsius and they're in a condition in here that's definitely going to be running pretty warm, you know, that's exactly where you want something that has a little bit higher temperature rating. So I think a better upgrade would be to change all of these. Now, I don't know these larger filter capacitors. I'll have to see what options are available for those. They might be a little bit tricky to find the right replacement. So, you know, I'll have to see what's available. The others I'm not worried about. Those should all be very easy to find, the 105 degrees Celsius equivalents. So I'll get all of that work taken care of, and then I'll be back and I'll show you what I've done. All of the new electrolytic capacitors have now arrived, so I can get started on installing all of these. Now, something that's important to take note of, if you look at the circuit board here, you can see some of these capacitors, like this one here, this one, and then there's several more over here, they're non-polarized types. So you can tell they're non-polarized. They have NP marked on the capacitor, and there's no polarity marking like the negative stripe on a polarized type capacitor. And then the board itself has no markings for polarity. You can see over here, wherever there's a negative side on the capacitor, it's denoted by the shaded in half circle on the board. So if you look over here, this is a non-polarized capacitor, but then, for example, this one is a polarized type. So it's very important when you're replacing the capacitors, if they're non-polarized, that they be replaced with a non-polarized type. There's typically an AC or an audio signal passing through these non-polarized type capacitors, where the polarized type is just a regular DC voltage. Now, when you're replacing capacitors like these, it's always important that you replace them with the same value, whatever the microfarad rating is, but the voltage rating can be equal or higher. You never want to go lower than what the original rated voltage was. Now, you want to, of course, go within reason. If it's a 25 volt capacitor, you want to use something that's, 25 volt, maybe 35, or even 50 volt. As long as it fits on the board, you're not going to use something like a 250 volt. It would just physically be much too large. Now, if you understand how the circuit functions and you want to change a value of a capacitor, as long as you understand what the effect might be, that's perfectly fine to do so. In this case, I did change the value on these 4 large filter capacitors that are on the DC rail. So this one, and then over here, these 2. So these original capacitors, you can see the marking here. I think it's on the side. It's 3,300 microfarad, 80 volt. They're 85 degrees Celsius rated. So I wanted to use 105 degrees Celsius capacitors, but I felt this value could be increased a little bit more, and it certainly wouldn't be a problem. Could actually improve the performance just a little bit. So after looking at what options were available, I did find these very nice Nichicon capacitors right here. So you can see these are 80 volt, but they're 3,900 microfarad, and they are 105 degree Celsius rated. So very high quality capacitor, and the lead spacing is the same. Now they are a little bit taller, and that's of course because they have a little bit more capacitance, so you can see that extra height. But that's not a problem. I did take a measurement. The highest point on the circuit board are these 2. They look like standoffs right here, but they're basically just acting as heat sinks. They're on the tabs of these voltage regulators, and this is the highest point on the board. And if you recall, that metal bracket sits over the top of this board. It has those 2 transformers that are mounted on top of it, so nothing can be higher than the top of these 2 studs right here. So again, these will not be a problem. They'll fit right in here very nicely, and they're just under the height of those studs. So I was happy that those would fit in there. So that'll be a little bit of an improvement as well, not only the higher temperature rating, but a little bit more capacitance. I felt they were a little bit light on the capacitance that they chose on there, so won't be a problem at all. But if you are changing the value of capacitors like that, you don't want to get carried away. Let's say you went to, if the size permitted, you went to something that was, say, 20,000 microfarad or some drastically larger amount. it could have really damaging effects on other parts of the circuitry. For example, the power switch, it actually might weld the contacts of the power switch because the inrush current would be so high, and it could certainly damage the bridge rectifiers or whatever type of rectification that they have in the circuit. And so if you did want to increase that capacitance, you would need to look at a soft start type circuit. And of course that gets into a whole redesign of how everything functions. So within reason, it's perfectly fine to increase the capacitance just a little bit. All right, so I'll continue on with reinstalling all of the new capacitors, and then when I have some more progress, I'll be back. All right, the main circuit board with all the new electrolytic capacitors is complete and it's reinstalled. So the next thing that I needed to do is look at that power resistor that was getting so excessively hot. So my thought was to relocate it off of the circuit board and use a little bit higher wattage resistor as well. So let me get you zoomed in here and you can see exactly what I've done. So the original power resistor was installed right down in here. Let me reach around this way here. So you can see there's an unused hole right there, and you can see some discoloration on the circuit board. And the other mounting hole is a little bit closer to this heatsink right here. So I wanted to move it away from the circuit board, and you can see the new resistor is mounted right here. So this is a tubular wire wound resistor. It's on a ceramic core that's hollow in the center, so very easy to mount. You can just run a screw through the middle. So there was already a hole in the chassis. You can actually see another hole right next to it right there. So I think there was an alternate fan bracket that could be mounted over there. So I didn't have to drill any new holes or anything like that. So there's a little short standoff that just raises the resistor up a little bit, and the connection of the ceramic body into the metal of that standoff and then ultimately down into the chassis acts like a bit of a heat sink. But of course there's a nice breeze blowing right over from this fan because the air is coming this direction and moving over to the heat sink. So it's going to keep that resistor very cool. That resistor is rated 5.25 watts or 5¼ watts. And the original resistor is probably a 3 watt resistor, so it is a little bit higher wattage as well. Now, because the original resistor was getting so hot, the solder pads have lifted off the circuit board on the back side of the board, so I couldn't attach these wires into the hole right there and then the other hole. So I just ran the wires around to the bottom side of the board and went back on the trace to the next solder pad that was in good condition and just tagged them on right there. So that'll work very well. A little bit of heat shrink you can see on the connection going over to the resistor just to insulate it. So originally, let me zoom you back out a little bit here. The original resistor, take a look over here, is right here. And this resistor measures 290 ohms. So if I take a look right here, get a reading on it like so. There's a little bit of corrosion. It's been so hot on that one lead. Let me try to get right there. There it is. So 290.5 ohms right there. You can see this lead, it's been so hot, it's all kind of gotten some corrosion, some issues going on there as well. So I wouldn't even want to use this resistor even if it, was working correctly, just with that corrosion on it. So this resistor being 290 ohms, I took that measurement and I thought, well, I have a 300 ohm power resistor right here that's the ceramic type. So you can see that right there. So again, it's hollow right there. Just put that bolt through the center, that little machine screw rather. 300 ohm resistor, and I think the wattage on this is probably a 5 watt resistor or something very close to that, maybe 6 watts. So I thought this would work well, and it would mount just exactly like the one that you saw over there. It could just sit on its side. So before I did any permanent installations, I took that resistor and I just made some test leads. I clipped it into the circuit and powered up the amplifier, and the fan ran for maybe 5 or so seconds, not a whole really long time, maybe not quite 10 seconds, I wouldn't say it even that long, and then it stalled. So this is 300 ohms, 10 ohms more than the 290, and I thought, well, that's odd that just a little bit higher resistance, I thought the fan might run just a touch slower, but it shouldn't stall. So I took this resistor out and I put this resistor and just clipped it back in the circuit, and the fan did the exact same thing. It ran for 5 or so seconds and then stalled out. I thought, well, that's a little bit unusual. Now, you have to remember that the fan over here that we're dealing with, this fan back there, so this fan is a typical brushless DC motor. So there's electronics in here that cause the rotating magnetic field on the stator, and it causes basically pulses around on the stator windings, and that's what causes the permanent magnets that are on the rotor that are attached to the fan blade to want to rotate and turn. But because there's electronics in there, that fan doesn't act the same way as a brush type DC motor. So a typical brush type DC motor, the motor might be rated, let's say 24 volts, but you could lower the voltage down to something very, very low, maybe as low as say 5 or 6 volts, and the motor would just turn very, very slow. It may not have a lot of power and all that, but it would still run. It probably wouldn't even stall until you got down to the very, very low voltages. A motor like this with the electronics will get to a point where it just stalls. It can't run anymore because the electronics won't operate correctly, but when it does that, it still draws current. And that current varies. It doesn't work the same way as the current draw on a brush type motor. So some different issues start to kind of happen. So with that said, I was looking at this original resistor, and let's go back over to that a little bit here. And I thought, well, if the original resistor is 290 ohms and that motor isn't working correctly, or wants to stall, is there something wrong with the resistor, or is there something wrong with the fan motor? So the fan motor, oddly, has no markings on it. I think the manufacturer may have intentionally taken the label off or just ordered them that way. So there's absolutely no specifications on that fan. I don't know the voltage or anything else about it. I don't even know who the manufacturer is. Normally the fan's on the hub, on the impellers or something like that, but anyways, it's not there. So I took a measurement of the voltage that's going to the fan speed control circuit, and it's 30 volts. And I put 24 volts directly to the fan motor, just unplugged it, used a separate power supply, and it runs very nice on 24 volts. And in fact, in the high speed setting, when that triggers and runs the fan at the high speed, it does actually apply 24 volts to it, and it drops just a little bit of voltage across the high speed resistor, which happens to be a 33 ohm resistor. It drops about 6 volts across that resistor. So that all seems to make sense. So it probably is a 24 volt brushless DC motor. And I didn't see any issue with the fan motor. Again, it seemed to work correctly. It wasn't binding up. It's not stalling when you just put 24 volts on it. And I actually found that you could put 12 volts on it with no issue whatsoever, but under 12 volts it stalls. So it seems like for a safety margin, maybe operating around 14 or 15 volts would be perfectly fine. But again, it's probably made to run on 24 volts. So I didn't want it to stall out in normal operation. I don't want to be on that ragged edge. So let's take a look at this resistor and see if there's something going on with it. Now we know it measures 290 ohms. We also know it's been extremely hot. So if you look at the color bands on this resistor, I don't think that they're actually accurate anymore, because with the heat that's been on this resistor, it may have had original color bands that looked a little bit different. For example, this one in the middle looks to be a white colored band, but it may have been yellow or some other color, and it may be faded or discolored because of that excessive heat that's on it. So resistors like this with the 4 bands on it, the 3 bands give you the value of the resistor, and then the 4th band is the tolerance band. So if you look at the resistor this way, this appears to be a brownish color over here, so I'd say brown is 1, white would be 9, red would be 2 zeros for the multiplier, so you'd actually have a 1.9 k ohm resistor, okay? And then this kind of looks like a silver color over here, and silver would be a 10% tolerance, so it seems to make sense. But this, no way would this have ever been a 1.9 k ohm resistor. A 1.9 k ohm resistor would drop far too much voltage in a circuit like this, so it's not possible that it could have ever been that value originally. And then if you take the resistor and you turn it over and read it the other direction like this, it really doesn't make sense, because there wouldn't be a silver over here, but you could maybe say that's a grayish color, so gray could be interpreted as an 8, red would be a 2, and white for a multiplier is not valid. There is no such number. And then the tolerance, I don't know, I mean, if this is brown, it could have been gold at one point, there would be a gold tolerance, but anyway, that doesn't make sense reading it that direction. Now, 290 ohms, the value it's actually reading would be a red, white, brown, but we can't get a red, white, brown any way we look here, because there's no red band on the starting point. The red is 1 band in this way and 2 bands over this way. So I have to think this resistor has changed in value. Now, I already mentioned I don't have a schematic for this, and this is where a schematic would be really nice, because you could just look at that and see what the original value was. So if anyone has one of these amplifiers and can look at that resistor, if it hasn't gotten excessively hot, I'd be very curious to know what the original value was. Again, 290 ohms actually doesn't work, because again, this is in the circuit, that fan stalls out. So I thought, well, let's see what it takes to make the fan run correctly. So I started lowering this resistance down, just trial and error, and I actually found that 150 ohms works very, very well. You can actually go to 160 or even a little bit higher resistance, but you get into non-standard values. So 150 ohms is a standard value resistor. and very easy to find. So that's actually what I've used. So the resistor that's in there is 150 ohms. It's made by Ohmite. Its part number is B5J150, so B5J150, and it's a 5.25 watt. So the wattage is a little higher than it needs to be, but no harm with that. So the actual measurements now with 150 ohms, you get about 14 volts on the fan, very, very close to that, and it's dropping 16 volts across that new resistor, and that's actually works out to 1.7 watts, and it's 106.6 milliamps. So very, very normal looking values, no issues whatsoever with any of that. So very happy with how that turned out, but I'm curious what this resistor should have been originally. And again, I think that its value has changed because it has gotten so extremely hot over the years in here. I have to wonder if maybe this ran for a while without that fan actually operating. So the next thing that I want to do is power up the amplifier and check its full power output, and let's make sure that there's no issues with the audio circuit portion of the circuitry. I haven't actually put an audio signal to it yet. So I'm going to get things repositioned, and let's hook up the oscilloscope. I'll hook up a watt meter and an 8 ohm dummy load, and let's check out the performance of the amplifier. Okay, let's check out the performance of the amplifier and see if it's functioning correctly. So just a quick walkthrough of the test setup that I have going on here. So starting way up here, move the camera up, pardon the movement here, you can see way up there where that patch cord is going is the signal generator. So that'll be producing the 1 kilohertz sine wave, or 1000 hertz if you like. So coming back down here, you can see this box right here has an unbalanced connection on this side, RCA type connection going in over there. And then the other side right here coming out is a balanced audio connection. So this is a 1/4 inch TRS jack, or tip ring and sleeve type connector. See this cord right here, just a short patch cord, and it goes over to the XLR connector right there. Now this is also, it breaks the ground connection from the input to the output. Another use of this box is for ground loop problems that introduce hum into audio signals, so it's useful for that as well. But in this case, I'm just using it to basically break the ground connection for safety and to change from unbalanced over to balanced. All right, so obviously we're looking at the back of the amplifier. That's where I need access to these various connections on here, and also the level controls right here. So I'll monitor the front panel where the status indicator lights are, but not a lot otherwise going on there, so it's easier to have the amplifier positioned around this direction. And then moving over here, you can say I have my Fluke 199C scope meter, so we'll monitor the waveform over here. And right here is an 8 ohm dummy load, 300 watt rating. And then right here is a watt meter, so we'll be able to watch the output wattage directly on this meter. Now, don't let the kilowatts fool you here with the scale, because the first tick mark over here is actually just 5 watts. So these values on here, you just multiply them out by 1 kilowatt. So the bottom scale is what we're reading, and goes from 5 watts over to 500 watts, all right? And yes, this watt meter has been verified accurate at 1 kilohertz. So I'll keep the camera focused in over here so that you can watch the watt meter and also the oscilloscope display. So, come up here. Let me reach around over here first of all, turn on the amplifier. You can hear the fan kick in there. There's a slight delay, relays clicked, so all looking good at that point. And you can see I'm just going to be adjusting this level control right here, and you can see the oscilloscope will auto range, and we do see a waveform over there. Perfect. So that's just 4.28 volts RMS. You can see it's right at 1 kilohertz, fluctuating there all nines or 1 kilohertz, no problem on that. So if I increase this a little bit further, it'll auto range. That's why it jumps on the scale over there. That's just the oscilloscope changing automatically. And you can see the watt meter is coming up, so that looks very good. And continues to increase. No problems there. So let me zoom the camera in a little bit closer here so that you can see the instruments a little bit better. So this amplifier has a maximum output into 8 ohms of 160 watts, so we want to make sure that it can achieve that. But we also want to look and make sure that there's no distortion or clipping prior to that on the oscilloscope display. And that sine wave, it should be just a perfect pure sine wave. And also we want to make sure that there's no crossover distortion, and we'll check that at a very low output signal, so I'll get to that in just a moment. So let's increase this all the way up here. And 8 ohms, or 160 watts into 8 ohms is 35.8 volts. So looks like if we go a little bit more, there's 35, 36. That's very good. So I don't see any clipping, and we are at 160 watts. So that looks very good. No issues whatsoever. That's a very good looking sine wave. If I drive that a little bit further, yeah, you can see the top and bottom on that waveform is starting to clip. You can see a little bit of distortion, a little bit more. Yeah, you can see the tops are starting to flatten out. So perfect. It meets the output power rating. No issues whatsoever. Turn that back down again. And looking very good on that channel. I don't see any issue whatsoever with that. So let me go all the way down here to a very low level, and let's just make sure that there's no crossover distortion. So decrease that. So I'm going to reach over here and just manually auto range this. Set the sweep time a little bit faster. That should look right there. So that looks very good. So you can see we have a 329 millivolt sine wave right now for the amplitude voltage reading. And the ground reference is where that letter A is right there. So through that graticule, that's the ground reference. And you can see that when it crosses the waveform through the ground reference right there, there's no step or distortion, and that's very important. So what that tells us is that the bias is working correctly in the output stages. There's no problem on the output stage, which is a push-pull type stage, where the transistors are switching, and we don't want to see, again, any crossover distortion. If the bias is missing or improperly set, you can get a step in the waveform, which causes a lot of audio distortion right there. So again, looking very good, no issues whatsoever. And when you're looking for crossover distortion, you want to check that at a very low output level, because that's when crossover distortion is most evident. So no problems whatsoever with this channel. Let me move things over here to the other channel, and then we'll check that out as well. Okay, I have the input going to channel 2, and you can see the output over here, pardon the camera movement, is now down here on the other speaker terminal connections. So let's increase this, and yep, there's no problem there. Well, I have the oscilloscope set to that range that we had before. Let's make sure there's no crossover distortion on this channel, and that looks very good. I don't see any step in the waveform there. Again, no issues with that. So you can see the output right now, 456 millivolts RMS. So yeah, that's looking very good. Back to auto range. Yep, and the watt meter is increasing. So it's about 100 watts right there. And let's see, we want to go 35.8. Looks very good. So you can see the watt meter is indicating 160 watts. Get you zoomed in a little bit closer again here. And the oscilloscope display looking very good over there as well. Pardon the camera movement there. So no problems with that. Yep, it's starting to distort right there. You can see the waveform flattens off, so about at the same point as the other channel was doing. There, about 160 watts right there, no problems. Yep, definitely clips right there. So that looks really good. I don't see any issue whatsoever with the outputs. The waveform looks very clean, no distortion otherwise. It meets the full power output specifications. So I'll spend some time going through some of the other frequencies and just making sure that the amplifier is performing across the whole audio spectrum correctly. If there's anything else that I find that's an issue or needs, any kind of attention, I'll certainly include that in the video. And if everything looks good, then I'll move on to the next part, which is a quick discussion about the constant voltage output, what's actually going on with that. If you're not familiar with that, you might find it interesting. So we'll do that next. Okay, let's see how the 70 volt output from the amplifier actually functions. So sometimes you'll see it referred to as 70 volts or maybe 70.7 volts. Sometimes you'll hear it referred to as a constant voltage output or a distributed audio system. the terms are used interchangeably, but constant voltage output, that can be a little bit misleading because it's not actually a constant voltage. It's not some type of a carrier voltage that's always present or something like that. A better term would actually be a high impedance output. So if you think of on the amplifier over here, we had the 8 ohm load, that would be a low impedance, and this is actually a very high impedance output. Now, this transformer, there's actually the two transformers, but this is a key to making this 70 volt output. These are actually connected from what would basically be the 8 ohm side over here. They tap into that, and then the secondary of these transformers comes over here to the higher voltage outputs. So this will do 25 volt, 70 volt, and 100 volt outputs. It actually will go to 200 volts if you bridge the two channels. But 70 volts or 70.7 is a very common distribution type system. So we'll take a look at a schematic in just a moment, and you'll see how all the components fit together. Now, move this camera over here, pardon the movement, but you can see the rest of the test setup here. I have the Fluke digital multimeter so we can measure some voltages. The Weston watt meter, like we had before, this will let us watch the wattage that's going to the primary on this transformer. I'll talk about this in just a moment. And then the secondary of this transformer is going over here to my Marconi 893C audio frequency watt meter or power meter. Okay, so this is set up like an 8 ohm dummy load. You can see it's on 8 right here, and then the ×1 multiplier. So again, this is acting like a resistive 8 ohm load, and this will let us measure the wattage directly, and it's set to 10 watts, so it's 0 to 10 watts on that top scale. Okay, so it's 1, 2, 3, 4, etc. over to 10. Now, taking a look at this transformer down here, this is really key to the whole 70 volt audio system. Zoom in a little bit closer here. Some markings on this transformer that are important to take note of. So you can see on the secondary side right here, there's a common terminal and then the various impedance taps. So you have 4, 8, and 16 ohms. So very typical values that you find for speakers. So I have it on the 8 ohm tap. So these two wires are going over to that Marconi watt meter. All right. Now on the primary side, this is coming from the audio amplifier. You can see I've soldered this wire. We don't need to move it. So it's on the common terminal. And then you can see the other speaker wire is just going to this yellow test lead, and it just clips onto the 10 watt tap. So we can move this around to try the different wattages, and you'll see the effect of what that has. So you can see there's a 10 watt, a 5 watt, 2.5 watt, 1.25 watt, and 0.62 watts. Those are actually really common values that you'll find on these transformers. And this is a fairly small transformer. Some of them go up to maybe 50 or even 100 watts, but typically on a distributed audio system, you're not driving any one speaker with a huge amount of power. So it's pretty common to find transformers about this size, but again, you might see them a little bit larger. Now, on a distributed audio system, the whole purpose of that is to drive multiple speakers, many speakers for that matter, and do it in such a way that it doesn't overload the amplifier or cause problems on individual speakers. So for example, think if you had a restaurant and you needed to drive many speakers around the restaurant. You might have something in the entrance, perhaps a speaker or two near a bar area, maybe several speakers in the dining area, perhaps some in a patio area, maybe several speakers near a bathroom area. Well, all of these speakers really start to add up, and if you connect, let's say all of them are 8 ohms, if you connect all of them in parallel, you're going to be very quickly down to just a fraction of an ohm, and there's no way that the amplifier could actually drive all of that. And even if it could, you'd have extremely heavy gauge wire. If you like to weld with the amplifier, then that's perfectly fine, but that's not very practical. In fact, really amplifiers wouldn't be able to drive that. So the amplifier we've been working on here is rated down to 2 ohms, but many amplifiers can't go that low. And even if it can go to 2 ohms, again, paralleling, let's say 10 or 12 8 ohm speakers, you're going to be down to just a fraction of an ohm, and it just won't work. It would overload the amplifier. Now, you can't connect the speakers in series either, because speakers that are connected in series can interact with each other if they have a crossover network in them. They won't play nice if they're connected in series, and they wouldn't necessarily drop the same amount of voltage across each speaker, which translate into various audio levels. So that definitely won't work either. And if you were to string, let's say, 10 8 ohm speakers together, even if they were all perfectly 8 ohms, you would be at 80 ohms. That value would be very high, and the speakers would play extremely quietly. And what you would actually need is the amplifier to produce a huge output voltage to overcome that high impedance so that the speakers would then drive to a better level. And obviously none of that is practical, and that's not the way the amplifiers are made. So now enters the 70 volt system. So it's a high impedance system, meaning that the voltage is higher. It's 70 volts. As we saw before, when the amplifier was hitting its maximum wattage on the output, it was about 35 just close to 36 volts, and we were getting 160 watts. Well, this is going to be closer to 70 volts, or right at 70 volts in most instances, when the amplifier is producing its full output onto these transformers. Now, on a distributed system, each speaker has one of these transformers, so that's a slight disadvantage. You do need to have a transformer with each one. That could be some added cost. Now, many speakers made for distributed audio systems will have a transformer included with them, but with this transformer you can take any speaker and then connect it into this 70 volt system and it becomes compatible. So let's take a quick look at a schematic, and you'll see how all of these components connect together, and we'll take some actual measurements and we'll see exactly how all of these components interact with each other. Here's a schematic showing how the various components in a distributed audio system or a 70.7 volt system are connected. So in this example, you can see there's 4 speakers that are shown, but in an actual system, you could have many dozens of speakers. Now, the limiting factor on how many speakers you can connect to a given amplifier is given by the wattage taps that you use up here. When you add all of those taps up, okay, so here we have 10 watts, 1 watt, 2 watt, and 1 watt, so that's 14 watts. That value that you come up with should be 20% under what the maximum wattage rating is of the amplifier. So that 20% derating is just a safety margin. It's a typical rule of thumb to follow. Now over here you can see on this dashed line, this is representing what's inside the amplifier. So this transformer right here would be one of those large toroidal type transformers that we saw in the amplifier. And there's 2 of them, one for each channel. So this primary side of the transformer right here is connected to the output transistors in the amplifier. And then of course this secondary side here, which is basically a step-up transformer. So we have a high impedance on this side, this is a low impedance on this side. Because the impedance is high, the voltage rises up, the current falls, and that makes this distributed system work very well, because these wires coming out here could be 14 gauge or 16 gauge, something very manageable. They don't need to be a real heavy gauge of wire, even though you may have, 100 watts or 200 watts or so of total load that's or power that's being delivered to the loads out here. But again, because the voltage is high, the current is low. So you can see on each of these transformers, this represents one of the transformers like the example that we're using in the test here. So you have the wattage taps on the primary side, and then on the secondary side, they're not showing the taps for the different impedances. We're going to use the 8 ohm tap, but some transformers are fixed for only one impedance, and like the one that we're using, it has multiple taps for 4, 8, or 16 ohms. So again, on this side, you select the tap for the wattage that you want. So on a 1 watt tap, this speaker is only going to get 1 watt worth of power delivered to it, where over here you're on 10 watts. So this speaker would be able to play louder, and you might want to do that just on the area that the speaker is in, if it needs to play louder than something where you intentionally want it quieter. And of course the size of the speaker, it may be a higher wattage speaker. Here they're showing an attenuator as well. You can start with 10 watts, you can attenuate that down. This is just a variable resistor. This would typically be on a wall plate by a door or another convenient location. So if you have an attenuator, we're not using that in this example, for the test setup that I'm doing here, but an attenuator is just a convenient way to have a volume control on individual speakers. Something like a horn speaker, very efficient. You would typically have that on a lower wattage tap because they play very loud. So very versatile in all of the different connections and combinations that can be configured. Now, something that's a general misconception is this 70.7 volt value up here. It's not a constant voltage like a carrier voltage or something like that. The 70.7 volts, you really will only measure something close to that if you have a pure sine wave that's being applied to the amplifier, which we'll have in the test that I'm doing here. So we'll be able to measure this voltage that's on the secondary side, but for typical audio, music, voice, things like that, this voltage is fluctuating, all over the place, and you're not going to see a constant 70.7 volts. All right, let's try the test on the amplifier's 70 volt output. Now, when I previously showed you the test setup, I had forgotten to connect the digital multimeter to the amplifier. So you can see over here the test leads are clipped onto the speaker output terminals right there, so we can measure the output voltage. Get you moved back over here to the various instruments. So I'll reach around and turn on the amplifier. So right here, the fan kick in there. And I'll switch on the signal generator, so it's still set to 1 kilohertz sine wave output. And I'll increase the level control on the amplifier. So we're seeing a voltage reading over there on the digital multimeter. So it looks good. Yep, and the Marconi watt meter is giving a good indication there. So I'll go all the way to full scale. That'll be 10 watts. Because again, this transformer is on the 10 watts tap. So that's indicating full scale, so that looks very good. And the Weston watt meter right here is also indicating right on 10 watts. So very reasonable. Now if this was exactly on 10 watts and dissipating 10 watts from this transformer into an 8 ohm load, this is set to 8 ohms, we would actually expect to see a little bit more than 10 watts going in because there's some loss in this transformer due to heating, but there's not enough scale resolution over here to really detect that, and it's just a very minor loss in there anyways. So it makes perfect sense that this is on 10 when this is also on 10. So the 83 volts over here, a little higher than that 70 volt value, but it's kind of a nominal value. And the amplifier is only lightly loaded. We only have a 10 watt load, one transformer, so that 70 volt value could certainly rise up a little bit as well. If I drop the voltage down closer to 70, lowering the level control on the amplifier, we can see right there very close to 70 volts. This has dropped down just a little bit, a little over 7 watts. Also, the tolerance in this transformer and its response at different frequencies could also vary the output voltage, which then of course changes the power dissipation. So a number of different factors, but for the rest of these tests, I'll go back up here to the setting right there where that's at 10 watts. So I won't touch the level control now for any of the further tests. This should stay very close to 83 volts. And let's move this to the 5 watt tap and see what reading we get on there. So I'll turn off the signal generator so there's no output, and move this over so you can see this is now on the 5 watt tap instead of that 10 watt. Again, that's the only change I'll make. Nothing else has been adjusted. Switch this back on. And look at that. So we have about 5 watts, just a little bit over, but very, very close to 5 watts. Makes perfect sense. So that's a good demonstration of how the wattage tap would affect the audio level or the volume on two speakers that could be absolutely identical. If you wanted one of them to play at a little bit lower level, you would just select the lower wattage or lower tap setting on the transformer. So very versatile and pretty cool system, and all the different ways that it can be configured. So I'll switch this back off again on the signal generator. And let's move this all the way over here to this lowest tap setting, the 0.62, so that's just a little over half a watt. Okay, I'll switch the signal generator back on. And we're still getting right about 83 volts over there, so that hasn't changed. Of course, this is a 10 watt scale starting at 1 watt here, so we have very little indication, but if I go down here to 1 watt, so this is 1 watt full scale. Half a watt would be right in the middle. This again was at the 0.6, I think it was 0.62, so that would be 0.6 is right there, and we're definitely getting over that. It's about 0.8, so a little bit on the higher side, but again, very reasonable, and certainly a lot less than it was when we were measuring 10 watts, of course. So the transformer is certainly doing its job and allowing us to select the different wattage settings and the amount of power that's then dissipated in the speaker, or in this case in the dummy load. So again, very versatile system, a lot of different ways that it can be configured, and if you're powering many speakers off of one amplifier, it certainly has a lot of possibilities and is very flexible in how you can set it up. So pretty cool system overall. The repairs on the Atlas Sound CP400 audio power amplifier are now complete. The amplifier is working very well, and it's definitely ready to put back into service. So if you enjoyed this video, remember to give it a thumbs up. And if you're enjoying the videos on this channel, please remember to subscribe. There'll be many of our videos like this coming in the near future. So all things electronics, solid state, vacuum tube, testing, everything about electronics, you're definitely going to find on this channel. So thank you for watching, and until next time, take care. Goodbye for now.